Hello, everybody. Good morning. I'm happy to be here and talk about the project Interstore and the distributed energy resources open source interoperability toolkit that we are developing in this project. But let me first share with you the agenda of my presentation. So first, I will have just a few words about the cybergrid. Then the flexibility challenges that we face when aggregating different flexibility assets. Then we will look into Interstore project and of course the open source interoperability toolkit. In cybergrid, we strongly believe that all energy should be renewable. And this is why we strive to unlock this flexibility from different assets. And one of the ways to do it is by using our software called CyberNOC. It's a flexibility management platform that allows basically to aggregate flexibility of different assets. On the picture, you may see that we can tap into flexibility of industrial commercial assets, then distributed generation, energy communities, batteries, and so on. And we can then monetize and utilize this flexibility for different use cases and on different markets, like balancing markets. We all know AFRR, MFRR, also wholesale markets, or for internal optimization of energy portfolio. And by doing this, of course, we face many challenges. And one of the main challenges that we face today, and of course, it is a significant obstacle for future or quicker development of demand response and flexibility monetization on the market, is the lack of interoperability or the difficulty to connect flexibility assets to such aggregation platforms. The existing protocols, many are obsolete. They lack features that we would need for efficient aggregation, and also security-wise, they are not up to date. And there is a growing need for really real-time data exchange, and also to have a possibility that this flexibility asset communicates not just with one energy management system, but maybe with two or even three. With the objective to basically remove these barriers, to some extent, we proposed Interstore project, where we would like to develop a set of interoperability tools based on IEEE 2030.5 that would help manufacturers on one side to easier and quicker deploy such interoperability protocol, and on the other side also EMS manufacturers to do the same. But if we look a bit some facts from the Interstore project, it is Horizon Europe funded project. It started last January, so it's basically 1 year since it's operational. The budget is 4.3 million euros, and it's coordinated by University in Aachen. In the logos below, you can see who are the partners. It's quite a diverse group of partners, and each of us has quite an important role to play within the project. As said, the overall objective of Interstore project is to enable distributed energy sources to seamlessly integrate with other energy management systems, and to allow for utilization and monetization of their flexibility. It has two pillars. On one side, we have open source interoperability software toolkit with also a connector to open data spaces. And on the other side, we have some enhancements and or we can call it also a new generation of energy and flexibility management systems, which are meant to optimize and make an efficient flexibility hybridization and monetization. With these metrics, you can see the link between different open source interoperability toolkit components on the left side with green color. On the other side with blue color, you can see different energy management systems that we are working on as a consortium and how they are connected to different pilots and also different use cases. If you're interested into more about how this works and what objectives or what issues each pilot is addressing, then I invite you to visit the Interstore webpage. At the end, I will also show the link to the Interstore website. Now about IEEE 2030.5. This protocol we selected in the project as, let's say, the most promising protocol for distributed energy resources to be connected for flexibility, utilization, and monetization. Current version is from 2018. It is gaining large traction in US. Australia has decided to be this national protocol. And in Europe, we can see also more and more traction in using this protocol. So it is object-based and IP-based application protocol for different inverters or charging stations and other distributed energy sources. It is built on REST architecture. And what is very important is also that it uses IEC SIM and 61850 data model. Additionally, it supports the device discovery, registration, and enrollment, which leads to hopefully true plug and play, which is something that we all wish that in the future the flexibility devices would simply be plugged and once connected to the internet, the aggregation platforms would be able to automatically discover them and also start using them. So a new version is expected in in this year, basically, and apparently it's going to support some of the changes that were made during the implementation in Australia, plus some other features that are going to be implemented. In green boxes, you can see different features of the protocol, but maybe if we focus only on the smart energy part, where you can see that billing, then demand response, messaging, smart metering, prepayments, pricing, all this stuff is supported out of the box. So what makes this protocol really convenient for modern smart grid applications and systems. But of course, since this is an innovation project, we are planning to go beyond the state of the art. We are proposing some improvements of the protocol itself. So instead of using REST, we are proposing NATS, which is asynchronous protocol. It is basically high-performance cloud-native messaging, and it's also open source and quite efficient and also secure. Yeah, and what it also supports, it supports that many-to-many connection. So since it's messaging protocol, basically many devices can talk to many different energy management systems. I will show you an example later on. And additionally to XML schema, we are also introducing JSON. Actually, it allows much faster data transfer of the same data. So it is quite more efficient than XML schema, and is especially suited for web applications. Here on this slide, you can see the architecture of the interoperable client server of IEEE 2030.5. So you can see that many devices can talk to many EMSs, and so this software will be developed using Java programming language and microservices. And it will be available on GitHub since April 2024, so this April. Here you can see many different communication scenarios. The first one, end-to-end messaging, is let's say the initial one, or the most simple one, where you can see that through the subject, which some of you may know as a topic, like in MQTT messaging, topic is used, but subject or topic, this is the same thing. And here you can see that this many-to-many connectivity is really supported. And with the next scenario, we can also use a reply option. So this would be like a dedicated subject just for the replies. And with the third scenario, we introduce also the stream object, which allows actually for more efficient exchange of time series. Like if we are dealing with some metering data that is flowing second by second or even faster, then we can use this special subject, which is called stream. Since in the field there are many devices that support different legacy protocols like Modbus or MQTT, we decided that it would be good to have also legacy protocol converter. So we are also developing this software, which will enable connection of these old devices that are using, for example, Modbus, to be connected to EMS systems that are supporting IEEE 2030.5. And the same like with the client server, this will be developed using Java microservices. It will be deployed as Docker containers or jar files, and on the GitHub you can download this from April this year on. And to make the whole package, we can't forget about the testing and the certification of the implementation of the standard. This is why one of the tools is going to be also testing software and procedures. And with this, we would like to offer a tool for certification authorities that might want to, offer a service of certification of devices that are using IEEE 2030.5 over NUTS. And it will allow end-to-end mock testing, testing message compliance and payload validation, and it will also be available on GitHub from April this year on. This is all from my side. Thank you. Here on this slide, you can also find the web page to Interstore or to CyberGrid if you're interested. And yeah, if there are some questions, please.
Should we leave the questions for the end?
Okay.
Yeah, Peter, then I go now. Okay. Okay, so the second presentation is focused on an actual distributed type of resources. So we thought of addressing this topic because in Interstore we have quite a rich environment, and one of the features that we are trying to show is how hybrid storage systems can perform, in what use cases they can have a higher performance when compared to a single system. And in the pilots that we have in the project, we have different configurations of hybrid systems. And right from the start, there was this challenge of, okay, if I want to dimension or to size a hybrid storage system, how do I do it? So it was a very simple question. So INESC TEC took on this task, and I will present to you the methodology that we pursued and the model that we've developed. Yeah, just a couple of slides to justify the pertinence of hybrid systems and storage actually for all the calls and all the projects that are running at the moment. I found these impressive numbers that the EU reported. So their expectations is that storage can be more than 200 gigawatts of energy storage installed capacity by 2030. So we are talking about 6 years away. And even more impressive, the numbers of 600 gigawatts by 2050. So there is clearly a recognition of the role that storage systems will have on the grid. And so even more if we think about these architectures and the distributed nature of these assets. I will cover these 5 topics. The way that we approached this task was by defining an initial set of requirements. I chose the main requirements to share with you, and then there are the next 3 bullets are basically the 3 main blocks of the model, and we end with a technology selection approach that could be taken after running the model. So for those who might not be so familiar with the concept of hybrid energy storage, there is not actually one definition, but they pretty all much tend to the same wording. And so this is basically a combination of technologies, can be of different characteristics, sizings, and the goal is that a hybrid system can outperform a single system. Okay. And so as for the requirements, we started by acknowledging these 4 points. So we thought that we wanted to achieve a different ratio of power to energy of 2 different storage systems with a resulting specific power that better matches the requirements of the application. So we chose one type of service here. So we needed to have this system applied to something in order to dimension it. Okay. Then we thought that, well, the goal here is to downsize the overall system when compared to a single system, okay, while retaining the original total energy and power capacities. So this, in the end, this is the magic of it all. We also thought that we would have to minimize the idle power or capacity. So if the system is to be applied to a certain type of load or service, it has to be a fit model. And this implies that the system will start and finish at the same state of charge, not necessarily 0, but can be 20, can be it can be a setting. The system also, the model also foresees different possibilities of dispatches of the batteries. We will see this in the second block. Also, we wanted to develop the model technology independent. So we didn't start by choosing the technologies. So this is something that comes at the end. Our goal is to look at the purpose of the system and define a power and energy capacity for the two batteries that can outperform a single battery, in this case, in terms of sizing. Now, we also thought that it would be effective if instead of only one optimal solution, this could provide several optimal solutions. And this is because we wanted this to be a practical model, and it had to match the existing commercial solutions out there. So it would be of very little use if in the end of the model we arrived at a couple of values, but those solutions didn't exist. So we thought that the output had to be quantifiable. And initially we thought of an array of solutions. In the end, we ended up with an area of solutions. So as an input, we have the historical load data set of this generic load that we are using that can be input as a CSV file. And we wanted the model to be released open source. And we developed this in a Python environment. And so just for the sake of simplicity, let's consider this simple connection. So we have a grid on one side, we have a generic load. In our case, we took as an example the load of a building of an industrial partner that we are working with. And we have a hybrid energy storage system in the middle that can support totally the generic load, or partially, or not at all. And our model is composed by these three blocks. So we will start by the recurring pattern identification. Then we will have a second block which makes an optimization of the battery dispatch. And then we have the actual hybridization model at the end. So why do we need to identify a recurring pattern? Well, we need it because we have to acknowledge that the battery doesn't support an infinite use of scenarios. So it needs to be applied to something so we can dimension it. So what we did, we took the load that we had from the building, and what we did was we applied a clusterization algorithm. So we saw that we could not use traditional algorithms such as the Euclidean distances. Instead, we use the dynamic time warping algorithm, which basically compares the load diagrams. And even though they are shifted in time, it's able to understand if they match in terms of profile, in terms of the drawing in the intraday. So what we did was we split our data set. We had 1 year of data, and we split that data in 365 days. Okay, and then we compared the days to each other. Actually, we removed 2 days, which was Christmas Day and New Year's Eve, because the building had no load, so we ended up with 363 days. And so if we look at the dendrogram that was that resulted from this clusterization, we can understand that the cluster with the highest number of observations that we can see here identified with this orange arrow is the cluster that has the most observations, so 210 out of 363. So this means that this is a recurring pattern here. There exists a recurring pattern, which will eventually exist in all data sets. But having a recurring pattern doesn't mean that all days in that cluster are the same. It means that these observations are similar to each other more than in another cluster. So this means that we can plot this in a box plot that we can see here in the top right. And we have, it's very informative, we can extract easily the maximum value of the power of all those observations, the minimum. We have the median values that we see here in the top left. And so from here, we can see already that the peak power is 232 kilowatt, and this one we have to fulfill this need of the observations that we require this power. And if we were to integrate this power over time, we would reach an energy demand by the load of 1,698 kilowatt hour. Okay. These parameters are the input for the next block, which is the battery optimization schedule. So as an input, we have the 232 kilowatt that I showed you in the previous slide. But in fact, we considered some slack, and this is a parameter that we can play with in the model. We considered here 8%, and this is to acknowledge that at a certain point we didn't want the system to have 100% load capacity. So, which means that we have a little slack, and we ended up working with 250 kilowatt instead of 232. But this is a parameter that we can set ourselves in the model. Then another input is the load. So we take the load from the median value that we saw in the previous slide in the blue line, and the other input is the energy capacity. But at this point, we are not sure what the energy capacity or the optimal value of the capacity that we could consider. So initially, we just considered the C rate of 1, and we took the value of 250 kilowatt hour as well. We run our optimization model that I will describe as well, and we get the battery dispatch for the next day that we can see here in the right side of the slide, okay, which is basically the 24 hours. We have the power input, the output, and the state of charge. The objective function in this case was we wanted to maximize the energy provided to the load okay, by our battery system. We can have different optimization functions for sure. This was a very simple exercise that we wanted to consider. Others can be used. So we have the constraints for this exercise. These have to be adapted, obviously, if you change the objective function. And as an output, so we have the dispatch, we have the maximum energy required by the load. We have the energy provided by the battery, which cannot be 100% because the battery has to charge at some point, so it will not be able to discharge at those hours. And if we divide one by the other, we have the load percentage that was satisfied by the battery. And so here we applied the load that you see here on the left. So this is a daily profile. And on the right side of the slides, we have the power input and output from the battery. So if you look at the negative part of the upper figure, you see that this is when the battery is charging, okay? And above zero, this is when it's discharging, so feeding, supplying energy to the load. And the bottom figure, we see the state of charge of the battery, okay? As the output also, below the figure on the right, we see that the total energy provided to the load by the battery, in this case, was 1,222 kilowatt-hour, but the energy demanded by the load was the previously seen 1,698, and this corresponded to 72%. But so we thought that, okay, so we have 72% of energy being supplied by the battery, but how do I know that this is the maximum that I can reach? Because we considered as an input to follow the C rate of 1, we consider 250 kilowatt-hour. So what if we change this? And so we ran the model. We ran the model again in a loop with different energy capacities with a step of 100 kilowatt-hour. From 125 kilowatt-hour to 1,700 kilowatt-hour. And then we got different percentages. Instead of the 72 that we got in the previous exercise, we got different percentages that we see here on the y-axis and the corresponding energy capacity considered in the while loop. And we obtain this curve. And so it's very interesting because it's similar to the elbow curve that is normally used for clusterization purposes, or the knee type curve. And what we see here is that there is a certain point where the marginal gains start decreasing, which means there is a point where I start increasing the maximum, the energy capacity of the battery, but I start getting less and less increase in the energy percentage supplied to the load, okay? And so in this case, there is this inflection here, where the curve starts bending around 450 kilowatt-hour. Okay, so we ran again the model with this value, and we get a new dispatch for our battery system. And this dispatch is the input for the third block, which is the hybridization of this battery. And so a bit of theory, just to frame what we did here. So if we consider an input signal, for example, this one at the bottom in blue, and if we consider a breaking point, so let's call it a cutoff of 50% of this signal here, we obtain two new signals that we see on the right. So one is identified with the green stripe, and the other one with the red stripes. So each corresponding to 50%. Okay. And from here, we can split this chart here in two, and we get the base signal and the peak signal. But instead of cutting this original signal in 50%, we can vary this cut-off range from 0.1 to nearly 100%. And so this results in theoretically infinite numbers of battery combinations, because we see here now that we can, instead of considering this generic signal, we will consider the signal will be the dispatch of the battery, okay? That we can see here. So let's say that that signal that I just showed in the previous slide is the battery dispatch. We can apply this cutoff of 50% or whatever we want, and we split the upper part and bottom part into peak battery, which has a designated power and energy, and also the base battery that also has an assigned power and energy. So if we apply different cutoffs to that same dispatch, what we will get what we see here on the right chart. We will get different powers and energies at 10%, 20%, 30%, and so on. The 50% here is represented, which we got from the left chart. Okay. And a bit more of a framing. So let's take the purple line that we see in the top right corner chart. If we take this purple line as a single battery that has an assigned maximum power and maximum energy, we see here two other vectors, the red one and the green one. So we can see that the red one is over-dimensioned in power, and the green one is over-dimensioned in energy. So it has more energy, okay? On the bottom image, we see that if we add the red and the green vectors, if we add them up, we will end up with the same maximum power and maximum energy of the original battery. And so if we play around with these two vectors, one will always be have more energy than power, and the other one more power than energy, we can end up with the same original power and energy of the single system. And so this is briefly the mathematical part. We initially started this exercise in Excel because it was easier to formulate the mathematical part, and we were able, once we were able to draw the hybridization curve that we see here in the chart that says hybridization curve, we thought that we were ready to move to a Python implementation. We leveraged on a study from the University of Hanover, which was quite useful also to understand the technical part, the mathematical part. And so we implemented this in Python, and the resulting curve at the end of our code is this yellow curve that we see here on the chart. So the purple line refers to the original battery, one battery only, and we get from the different cutoffs that we do to the dispatch signal, we get the yellow curve. And what does this mean when looking at this? It means that there is an area between the yellow curve and the purple vector with infinite combinations of batteries. So the way to read this is that we have, if you look closely to the figure, you will see that we have two y-axes and two x-axes. So the combination of one y-axis and x-axis refers to one battery, and the other one is basically inverted. And when they meet, so we can see here the point in the green, the green vectors, when they intersect, this is the optimal combination of batteries. Okay, so here we have two examples, we have two solutions. One battery, the base battery with 80 kilowatt and 110 kilowatt hour, and the peak battery with 170 kilowatt and 367 kilowatt hour, which is the green point at the green dot here. But we have a second solution, which is outside this optimal area. So it's outside the area that is enclosed by the yellow curve and the purple line. So it's this one. The red dot here corresponds to this second example of a base battery of 200 kilowatt and 200 kilowatt hour. And the peak battery, that is this one, has 50 kilowatt and 277 kilowatt hour. So here, 50 and 277. This is not an optimal solution. Okay, so we also met this requirement, which was to have different optimal solutions. So in case we look into the market and we don't find this optimal solution here that we see as solution one, we just look around other potential combinations that we can find in the market. The last challenge that we had, actually, the challenge was launched by Cybergrid, was for us to look into the technology selection part. So if we take those two examples that we had in the previous slide and we put them in this Ragon plot, I mean, in these type of batteries that we looked into, we can have different possibilities. We can have one battery being of lithium technology and the other one of vanadium battery, for example. And so they will have, it really then depends on what extra functionalities do we need from the batteries and what other services eventually that they can support. But so this is how we match the model, what exists in the market, and then the applications that we want them to have. This is also to acknowledge the fact that they have different discharge capabilities, if they are able to respond faster or slower to the set points that we impose. Yeah, I don't think we have time for the live demo, but I will invite everyone that wants to run the model to access our GitHub of the project. So you will find it in Horizon Europe Interstore. The model is there with this example, the very example that I've shown. You are free to provide any suggestions, any improvement recommendations, and to build on it. So from my part, that's it. We will take questions now, right, Peter? We had actually, we can start by a question addressed to you, which was how can an aggregator coordinate the triggering of the assets for flexibility provision, right? Was somewhere around this idea.
Yeah, thank you. Interesting question. So when trying to aggregate and monetize the flexibility, of course, we need to monitor the assets. So preferably having real-time measurement data, so that we can see what state the generation or consumption is, that we can better forecast also the future generation or consumption, as well as do the flexibility prediction. Based on all these data, we can then provide bids to different markets. Once the bids are accepted, we can reserve these assets. And when activated, we already have assets reserved and ready to receive the dispatched signals. Of course, at the moment, we are not yet talking about, millions of these assets being connected to an aggregation platform. So for now, we don't see any issues with like synchronous dispatch of these signals and also activation of the assets. Of course, we recommend that for each activation, there is a certain amount of reserve flexibility within the pool, within the portfolio. So in case some assets do not respond because of any possible reason, then there is additional capacity that system engages automatically in order to follow the required set point. However, if we look into the future and if we assume that in the future we will have to deal with millions of distributed energy assets, there of course might be an issues or bottlenecks in terms of communication protocols. And this is one of the topics that was looked upon also in IEEE 2030.5. And as far as I know, this is also one of the features that a new version coming out this year will somehow support. So the protocol, the standard is evolving and is also going to support more and more assets simultaneously. Thanks.
Okay, thank you, Peter. So I had a question also for me, which was, what was the impact? What would be the impact on the hybridization curve if we consider the different optimization exercise? Yes, this is a very pertinent question. So the model was developed in blocks, so it's a modular model, and so we can in fact apply a different optimization problem here to my battery. Of course, it will change the dispatch for sure, and this will have a different impact on the third block. And the way that it changes is that in the end, I will have a different optimal area. So the area between the hybridization curve, which was the yellow curve, and the purple line, this will change. It will be, we will have a larger area or a smaller area. Of course, then it will have a direct impact on the available combination of batteries that I have available in the market. A typical optimization exercise which is done for batteries is to minimize the energy cost of supplying that energy. It can be also minimize the emissions. So we ran a couple of these optimization functions. We thought that this would be a very simple optimization function, the one that we presented, so we went along with this one, but you are okay to change the code with your own optimization. Yeah, just have in mind that it really depends on the application that you want this hybrid system to have. Yeah, I see that we are pretty much on time, Peter, so I will invite everyone that watches this session to reach out to us with more questions to our emails. And I wanted to say thank you, Peter, for your availability. It was a very nice presentation. I think the idea was passed on.
Thanks for inviting me.
So thank you, and make sure you attend the next sessions of the power and energy webinars. Have a nice day.
Thank you. Bye-bye.